Welcome back, Chemistry 30. This is the MS1.4 Bond Polarity and Electronegativity section. So here we're going to use electronegativity differences to identify nonpolar covalent and polar covalent and ionic bonds. So up to this point we looked at ionic bonds, we looked at covalent bonds. Here we'll see that you kind of break down covalent bonds in terms of nonpolar or polar. So if you look over here, when two identical atoms bond, such as some of the Hofbrinkel elements, Cl2 or H2, the electron pairs are shared equally. Because you can think of, we have two, if it was a tug of war, having a set of two twins pulling against each other, assuming they're at the same body strength, it'd be equal sharing. When two atoms from opposite sides of the periodic table, such as NaCl, there's relatively little sharing. So the chlorine pulls all of the electrons in its area because sodium wants to lose it, chloride wants to take it, so it's a complete opposite spectrum. It pulls all of that off, and it ends up being sodium loses, chloride gaining. The outer electron of the sodium atom is completely transferred. But if we look at bond polarity, with especially covalent bonds, we're going to look at how equally or how unequally the electrons are shared in nonmetals that are bonded together. So if we talk about the two different types here, we have nonpolar covalent, which is one in which electrons are shared equally, such as chlorine and nitrogen. In a polar covalent bond, there's a greater attraction for one electron from one atom than the other. If the difference in relative ability to attract electrons is large enough, then we get a complete pulling and we have an ionic bond formed. So here we're kind of digging a little bit deeper, looking at ionic bonding, a complete transfer. Covalent bonding is a sharing, but within that sharing there can be equal sharing or unequal sharing. To understand polarities, a method needed to be devised to determine how effectively different atoms attract electrons. Linus Pauling developed the concept of electronegativity to numerically represent the ability of an atom to attract electrons. So that's what we mean by electronegativity, the ability of an atom to attract electrons. The figure below shows how these numbers come into play. So the larger the number, the greater the attraction. The larger the electronegativity number, the greater the ability to attract electrons. Sorry, I went kind of down the road there with this one. So you can see here that fluorine has the most. And that makes sense because fluorine, if we look at fluorine, it has its atomic number 9, which means fluorine has 9 protons in the middle, in the nucleus, and then we have even if you just imagine a Bohr diagram, it needs one more. And it's a small atom, so these 9 positives in the nucleus are very close to the outside, and they attract that electron quite easily because that nucleus is exposed to the outer area. Whereas if we go down, all of these need one more electron as well, but as you can see, electronegativity decreases so that when we get down to iodine, there's so many levels on there that these, even though I have, with iodine, I have like 53 protons, they're so deep in that atom, they're not going to have a great effect on pulling that electron in. Okay, so the larger the atoms, the lower the electronegativity. And of course, going from left to right, 0.81, you can see the numbers generally increase as we go from left to right. Because as we go from left to right, fluorine only needs 1, oxygen needs 2, nitrogen needs 1. So there's a strong attraction to complete it's being stable by achieving that noble gas state. So we have this chart of electronegativities. Also, I'm going to give you one, if I haven't already, one that goes 2 decimal places opposed to 1, so we could use this one. And of course, notice the noble gases have 0. They don't need to gain or lose. So over here we have francium, which is 0.7, one of the lowest ones, and fluorine, actually a little bit less than 4.0, 3.98. So looking at this, as seen on the table, electronegativity generally increases from left to right in each period or row of the periodic table. In addition, electronegativity within each group generally increases from bottom to top. Because the atom's getting smaller, those inner protons have a greater pull on those outside electrons. This is one of the most important diagonal trends when we go from the lowest number in the lower left corner to highest in the upper right corner. In a bond, the element closest to fluorine will be relatively negative as well, and the element furthest from fluorine will be relatively positive. Polarities are indicated by using these symbols, delta plus and delta minus. So the Greek symbol delta is used as, you can think of it as partial. A partial positive pole and a partial negative pole. Okay, so that's the symbol that we use to demonstrate that. Full positive and full negative charges will be used only for ions, in which we have a complete pull or a complete giving up. For example, boron oxygen would be written like this. And that makes sense because if I look over here, if I look at this table, oxygen is 3.44, boron is 2.04. So of course, which one's bigger? Oxygen. So it has the stronger pull for a shared pair of electrons. So we show that as, well, oxygen is going to be slightly negative because it's going to have the electrons in its area more often than boron has those electrons. So we show that with the little delta symbols. The electronegativity table seen in the previous page gives numerical data that may be used to evaluate the magnitude of bond polarity. This is done by subtracting the atom with the smallest electronegativity from the larger one, of course. The larger the difference in electronegativity between the two atoms, the greater the polarity it will be. If the difference is 0, we consider that equally shared, so that would be nonpolar. Without an electronegativity, you could still possibly determine which of two bonds is the more polar if the bonds have one common ion or one common atom. The more polar bond will be the one in which the second atom is the furthest from the first. So for example, if we're comparing a nitrogen and fluorine bond compared to an oxygen and fluorine bond, all we need to do is just look at a regular periodic table. NF versus OF. So NF versus OF. So you can see here that, well, the NF bond must have a greater electronegativity because N is further away from F. Then if we look at the electronegativity table, we will see that that is in fact true. So over here, OF, 3.44 compared to 3.98. So I could do the subtraction there and get a number. But if I look at here, 3.04 and 3.98, subtract that, there's a difference of 0.94 there. So that would be the more electronegative bond because it's further apart. Since nitrogen is further from oxygen. All right. So electronegativity and ionic character. So here's where we kind of look at, okay, so how do I know what difference is going to be what? Well, that's where this comes into play. So at one end of the scale, we have completely nonpolar bonds between diatomic elements, and then ionic compounds can be visualized as being on the other end of the polarity scale, in which we have a complete pulling of an electron from one atom to another. If the differences in electronegativity of two elements is greater than 1.7, then we consider it to be ionic in nature. So we kind of have a number that we can go with. If the difference in electronegativity is greater than 1.7, it's virtually ionic. And if the difference between the two bonds is 0.4, we could consider it to be nonpolar. And then anything in between that is going to be covalent. All right? So I think what I'll do is I'll stop there. And in the next video, we'll look at maybe copying out this data onto this piece of paper. Or if you don't have this yet, just copy it out somewhere so that when you do get this electronegativity table, you can put it on here. And then we'll look at a couple of examples from the assignment, and then you'll be set to go with that.